All right, let's dive into an AI that starts out by solving one of the most annoying little problems in tech, and somehow ends up in a place you would never, ever expect. A doctor's office looking at medical scans.
You know this pain. We've all been there. You're trying to copy a paragraph from a PDF, or maybe pull some data out of a table in a report. You highlight it, you copy it, you paste it, and what you get is just garbage. A total mess of broken lines and jumbled up words. It's maddening.
It seems like it should be so simple, right? It's just text on a page. So what gives? Why have computers struggled for decades with something that feels so basic? Well, the answer really comes down to how we've been teaching them to look at a document in the first place. So here's the fundamental problem. The old way, traditional OCR, uses what's called a raster scan. Just think of an old printer, going line by line, left to right, top to bottom. It has zero understanding of the layout. It doesn't know that's a column or that a caption belongs to an image. But that's not how we read, is it? Our eyes jump around. We follow the logical flow of the information. And that simple difference is the reason for all that jumbled text. And this brings us to a new model called DeepSeek OCR 2. Suddenly, people in the AI community started asking this exact question. How in the world did they manage to crack a problem that seemed, for all intents and purposes, unsolvable? Because this wasn't just a small improvement, it was a total game changer.
So, let's get into their first big innovation. And it wasn't about just recognizing characters a little better. No, it was about teaching the AI to actually understand the structure of a document, kind of like we do.
They came up with this thing called visual causal flow. Now, instead of that rigid top-to-bottom scan, the AI first just kind of looks at the whole page. It gets the context, the whole layout, and only then does it start to read, following the logical path, jumping across columns, grouping tables, connecting the dots.
And look, this isn't just a cool theory. It has a huge, measurable impact. They saw a 33% reduction in what's called reading order edit distance. It's a technical term, but it basically means the AI made 33% fewer mistakes in how it pieced the text together. The output isn't just a string of letters anymore. It's coherent information in the right order.
But here's the thing. Having a really smart model is great, but if it's super slow or costs a fortune to run, then what's the point? So the second big breakthrough here is all about making this practical, and I mean massively practical.
It really all comes down to tokens, which is basically the currency of AI. Every little bit of data an AI processes has a token cost, and a single high-res image, that can generate over 4,000 of these visual tokens, which gets very expensive very fast. What DeepSeek did was build this incredibly aggressive compressor that takes all those tokens and squishes them down to just 256.
That's a 16 times reduction in the data the AI has to churn through. And here is the absolutely wild part. It does this while keeping 97% of the crucial information. So you get this massive boost in efficiency without really losing any accuracy. It's incredible.
So what does that efficiency look like in the real world? It means a single group of servers can process over 33 million pages per day. This isn't just a lab experiment anymore. This is an industrial-strength engine for understanding documents. So we have an AI that can read documents logically and with mind-blowing efficiency. But this, right here, is where our story takes a very sharp, very unexpected turn. Just think about it for a second. If you had this kind of technology, what's the first thing that pops into your head? What would you use it for? You're probably thinking of all the classic stuff, right? Automating invoices, sifting through legal contracts, digitizing mountains of old archives. And yeah, you'd be totally right. But the researchers, they started thinking, what about a totally different kind of document? What if you decided to treat a chest X-ray as a document? Now that sounds crazy, doesn't it? I mean, one is text and tables, and the other is a medical scan of a person's insides. What could they possibly have in common? Well, this is the result. They took their DeepSeek OCR model, a model that had never, not once, seen a medical image in its life, and they tested it against other AIs, including ones built specifically for medicine. And what happened was, well, it was just astonishing. On a key test for generating radiology reports, DeepSeek OCR didn't just hold its own. It actually came out on top. It beat MedJama, a model that was trained on over 33 million medical images. A document reader was better at reading X-rays than a specialized medical AI. I mean, how is that even possible? The answer to that question, it turns out, reveals something much deeper about how information works and about what makes a truly powerful AI.
And here it is. This is the aha moment from the research paper. A chest X-ray isn't just a random picture. It has a predictable layout, like a form. It has a hierarchy of information: lungs, heart, ribs, just like a table. And to understand it, you have to extract very specific, dense details, just like reading a document.
And you can literally see it learning right here. Before they showed it any medical examples, the model was pretty bad at finding things. But after fine-tuning, its ability to pinpoint specific anatomical locations shot up by 262%. It was learning to apply its document reading skills to human anatomy.
And this really gets to the core lesson here. DeepSeek didn't win because it knew a thing about medicine. It won because its fundamental architecture for understanding structured, visual information was just better. It tells us that sometimes the foundation of an AI is way more important than the specialized data you feed it.
And that, of course, leads to a really fascinating question. If a chest X-ray can be read like a document, what else can be? Financial charts? Satellite images? Engineering schematics? The possibilities for this kind of thinking are just huge.
But, maybe the most mind-bending idea of all actually comes from the researchers themselves. They suggested using this same compression technology not on documents, but on an AI's own memory, to let it hang on to massive conversation histories by storing the older parts at a lower resolution, kind of like how our own memories fade over time. The next great challenge for AI might not be teaching it what to remember, but teaching it what and how to forget.